welcome to our LMI webinar series. Today we have with us Chris Yijun, Senior Director of AI Solutions, Trevor Ditrani, Software Engineer at LMI, and Yijun Jiang, AI Modeling Engineer. So this is part 2 of the AI webinar series, but you did not have to see part 1 to be able to follow today. Chris will talk about that a little bit. So today we're going to talk about the gadget configuration and deployment in AI. So just a few notes before we get started. This webinar is being recorded, so if you need to leave for any reason, you can watch this later. You'll get an email with the recording about 3 to 4 hours after the webinar. So just keep an eye out for that, and if you don't see it, check your spam folder. On the right-hand side, you'll see a chat function. And if you have any questions during the presentation, please put your questions in the chat, and we will do our best to answer all your questions. We will answer questions after the presentation, so if we don't get to you right away, just be patient with us. Yeah, but that's really all you need to know. So without any further ado, Chris, take it away.
Thank you, Vanessa. So good morning, good afternoon, good evening to everybody out there, and thank you for taking the time out of your day to learn a little bit about the LMI AI Solutions, in particular the Inspection Gadget software platform. So by way of introduction to this presentation, this is what we're going to cover today in intro to really the reason that we're doing this presentation today, some of the mega trends out there, and why we think this work is important. We'll do an overview of the Gadget software platform, and then a little bit of a primer on Docker and virtualization because it's an important part of the architecture. And then we'll apply the Gadget configuration, discuss some of the supported sensors and how they're used, and then we'll walk through the pipeline customization for the same model that was developed in the first part of the webinar series, and then we'll conclude by deploying the Gadget so that you have some ideas and familiar with how you might deploy your own models using this platform. So who is LMI AI Solutions? So we're a group at LMI that provides a turnkey AI inspection-based solution. And I show the typical solution in the figure to the right. And on the top, you see the automation systems and the vision systems. Those are the parts of the system that generally speaking already exist. The automation systems could be a PLC or a robot downstream, and the vision systems could be a 2D or 3D vision sensor or camera system. And so the inspection gadget communicates both to the sensors, and we'll talk more about that, but also to the downstream automation, usually over an Ethernet protocol. The lower 3 peers in this diagram represent the services and software that LMI makes for AI-based inspection. So from left to right, the model pipeline development service is something that we do for our customers, and what that means is that we work with customers to develop model pipelines using mostly open source software technology. We do things like gathering data, labeling the data, doing model pipeline design, training, validation, and then optimization for a hardware platform. So for some customers that don't have the resources on their team to do this work, we do provide model pipeline development as a service. The part that we're going to focus on today is the inspection device with the HMI, which is the LMI inspection gadget. And what that is the software platform that we use to deploy those models in a production factory environment. And it's like we'll talk about, it supports different types of hardware platforms. It does include a browser-based HMI, and really it's designed with AI-based inspection in mind. And then the last piece is the cloud services. That is also a service, can either be on-prem or a traditional cloud service like GCP or AWS. And what that does is that enables the system to be connected to a cloud service, again, either on-prem or in the cloud. And that system would be reporting data, including images and telemetry data, performance data, so that um, any stakeholders in the inspection can log in, look at performance of the system. We can generate alerts and also gather data that can be used to retrain models and then push those models out to the edge where the inspection is. So that's a summary of, again, the products and services that we make at LMI. And with regard to the inspection gadget, we really do believe it's the only open platform out there. And we'll talk more about the API and how we get from a custom model to something you can deploy in your factory. So this is the second of a three-part webinar series. The first webinar was back in January, and what we did there was we looked at an application inspecting defects in early stages of a catheter product, and we developed a model pipeline based on the YOLO V5 object detector, and then we stopped basically with a trained model. And so if you're curious, please go back and watch that webinar. It's a useful starting place, but like Vanessa said, it's not a requirement. So in today's webinar, what we're going to focus on is taking that model pipeline and deploying it to the gadget so that it could actually be used in a production environment. And in part three, we'll talk about the cloud services and how that can be helpful. So why are we here? And we reviewed this a little bit in the first presentation. Well, so what's happened over the past, let's say, 10 years is an explosion of new innovations, and in this case, publications or new technology that can be used for AI-based inspection. Most of this is around convolutional neural nets. There's new architectures that are emerging now. But the real interesting part here is that, well, there's a couple things. First, a lot of the technology that's being developed for different applications, and I'm showing three here, for self-driving cars, medical imaging, and social applications, that technology can actually be used, and many times it is the same technology that's used in diverse applications. So for most of our customers that are concerned about factory inspection, a lot of that same technology can be applied to solve your inspection problems. And in the middle, what we're showing is the rate of the growing rate of new contributions to this technology. And what's really different in AI deep learning technology compared to traditional computer vision is that the community that's developing the models is actually opening up the IP, and in fact, the software that is being used to develop that technology and making it available in places like GitHub. So that's to say that the technology is freely available if you're able to use it. And the other thing that's happening is companies that are investing in hardware, primarily GPUs, are innovating also at a very rapid pace. And so in this webinar, what we're going to focus on is how you can take some of these open source models that have been designed for your application and deploy them on some of these state-of-the-art hardware platforms in a way that's both robust and relatively efficient and cost effective. So let me go ahead and show a quick demo before I hand it off to my colleagues to show you how this process works. So here's an application that we've got running, And like I mentioned before, this is the Gadget app, which is the HMI that shows the AI-based inspection running. You see in the middle screen that we're finding defects in the catheter, and Yijun will talk a little more about that model. And again, it's an extension of the work we did in the first webinar. But you see we're able to find the defects, and in this case, the images are recycling. We've got the sensor running in a emulator mode so that the system isn't actually connected to the sensors themselves for this particular demo. But otherwise, this application is completely live. So in the model, in the pane here to the left, we have options to configure the inspection. We've got the sensor tab, which is open now, so that at runtime, the operators might want to change things like gain or exposure time to optimize the imaging. Certainly, you can tune the model to be very insensitive to things like that, but at the end of the day, those are parameters, common parameters that are used to get good 2D images. Might be more interesting for this case is looking at the model configuration pane here. So what you see is that we're finding the defects that this model was trained to find, and there's a score associated with the defects, and that's a confidence. So you can actually come in here, and this might be something that the operator might do, where we can change the confidence to say 1, which is the upper limit of the trained model. Let's actually still try to find the catheter, so we'll keep that one at 0.5. The other defects, we'll update this, reset the event counter, and look, now we're not finding any defects because we've taken the threshold and we've moved it to the upper limit. So this is just showing that, and you can see this from the charts as well, we're not tracking any of the defects, we're not counting any of the defects. You see some indicator lights down on the bottom. Those show that we're engaged. We're actually connected to a sensor. In this case, the sensor is a Allied Vision camera running in emulator mode, and then the model is loaded. We don't have any connectivity to an automation system right now for this demo. If we did, that would be green. And again, the subject of the next webinar is the cloud connectivity, and that would also be green. So let's go ahead and turn this back to something that will be useful to see the model performing. Here now we're finding the scuffs. And let's look at the peeling defects. Let's set that confidence at 0.8. So now we're finding both the scuff and the peeling, and we're tracking them on the right. So that's a quick demo of the Gadget app. Under the hood, it's running the Gadget platform, and I will hand it to my colleague, Trevor Ditrani, to talk about configuration of the Gadget inspection system.
Hi, Chris. Thank you, Chris. So I'm going to start with just giving a little bit of an overview of the Gadget. So the Gadget is our solution to the problem, I have a model, how do I get it into production? It's a hardware-neutral inspection platform that takes advantage of containerization, so it can be very modular, so that every application can be customized to fit its specific problem. It also includes a browser-based HMI, which you just saw, called the Gadget app for monitoring and configuring. Here we have a high-level diagram overview of the Gadget. Each box represents a container. These are the most important services for your inspection. As you can see, information is flowing from the camera on the left through the containers, and then finally a decision is sent to a machine on the factory floor. Each one of these services is also speaking to the Gadget app and keeping the user updated with the information about the system. So we've mentioned Docker and containers a few times, so some of you might not be familiar with it, so I will be talking a little bit about that now. So Docker is an easy-to-use virtualization platform, and it's the containerization technology that we use for our application. We use this so that the gadget is not dependent on the host system and can be easily deployed on almost any hardware. The container images are defined using Docker files, and then the group of containers that make up the gadget are defined using Docker Compose. Next, I'm going to share my screen and walk through a little demonstration of how to use Docker files and Docker Compose. So this is a simplified version of our model pipeline Docker file. As you can see here up top, this is where we define what base image we are extending. In this case, we are using a image given to us by NVIDIA. And then here we are installing all the requirements that we need for our solution for this demonstration. And then we are also cloning a Git repo. This one is our repo, our public repo that has a lot of helpful tools. And then this is the Docker Compose that you're using that is defining the container. The Docker file defines the image, and then this Docker Compose defines the container. Here you can see we are defining which Docker file and image to use. And then down here you see what command we are given the container to run. In this case, we're running NVIDIA SMI, which is a useful command to help to inspect the GPU of the device. So at the command line, we're going to build the container, the image, with the command docker compose build. See, we have built the image, and it was that image was tagged with this name. And then we are going to run the container, bring the container up, and it will run the command NVIDIA SMI. And if everything works correctly, we will see that the output of that and a little information about our GPU. And as you can see, it was successful. So this is the host machine that this is currently running on. So hopefully that gave you a better idea of what Docker is and how we're using it. I'm now going to talk a little bit more about how the gadget is set up and configured. Unfortunately, I lied a little bit before. The other diagram was not the whole picture. Here is a much more detailed description of how the gadget works. And most importantly, it has a more detailed description of how communication is done between containers. So as you can see, the mission critical containers for an inspection are the sensor, the pipeline, and the automation. And messages are passed between those containers using 0MQ, which is a low latency pub/sub messaging protocol. Image data is also shared between those containers using Docker volumes. And then finally, for all non-inspection critical communication, it happens through our REST-based database API that stores information into a Postgres database. This is how the Gadget app is able to monitor the system without getting in the way of the important parts of the inspection. All right, so now I'm going to show you our Docker Compose that we use to configure our gadget. So this is what it looks like. You can see that these top several containers here This is the Gadget platform that is running underneath that is supporting the inspection. These containers here are the mission critical containers that are defined for your inspection. We're going to take a look at the pipeline, which you'll notice looks pretty similar to the example you're looking at before. We define the Docker file that the image is built off of. We also define environment files to use for this container. And then we also mount certain volumes that we need for this container. And then we have a command that is run when this container is loaded. So the communication that I had mentioned in the previous slide is defined here in the Docker Compose and is also part of environment variables. For sharing images between containers, we do it through Docker volumes. So at the bottom of this Docker Compose, we have defined this image archive volume. And then for the pipeline, we have mounted this volume. So it'll save its images into this volume, and it will be accessed by any other container that has also mounted this volume. The other configuration is done using environment variables. So you can see here, we have defined an environment file that we are using. So if we go over to that, we can see these are the environment variables that we define for this service. Some important ones to point out is here we have the database API host and port, which is used for the REST-based database API. And then also the 0MQ subscription topic is the topic that this service is listening to. The rest of these environment files are initial values that are used by the service at startup. So I'm going to talk a little bit more about the sensors that we support. Out of the box, we support a number of industry standard sensors. Of course, we support the LMI Gocator for 3D inspection, but we also support a number of 2D sensors, including Allied Vision, DALSA, and Basler. And we've also worked with customers to connect the Gadget to their third-party software and receive images that way. Each sensor is different, and each vendor provides different software and APIs to communicate with their sensors. The Gadget allows the user to configure the sensor using the vendor's provided software, and then the Gadget connects to the sensor using the sensor's API. All our sensors are built off a base class, which handles the code that is universal between sensors. That makes it easy for us to add support for new sensors when needed. The Gadget can also be a multi-sensor platform. The modularity described earlier makes it easy to add multiple sensors to an inspection, as well as mix and match different sensor types in the same inspection. We're also able to have multiple pipelines running that are communicating with either all or just a subset of the sensors. All right, on that note, I'm going to hand it off to Yijun, who's going to tell you how to create a custom pipeline.
So thank you, Trevor. So this is what we left over on the first webinar, which is we want to detect 3 kind of defects on the catheter. So the first defect is on the left, which is peeling. And the second is in the middle, the scuff. And the last one is on the right, the white. So there are 2 ways to approach this application. The first way is the object detection. As long as we have the defect data with some labelings, we could use the object detection algorithms. The other way is the anomaly detection. For the anomaly detection, you only require the good data, which means the data without any defects. For this particular application, we found out that the data is a little bit noisy, so it will be a not perfect fit for the anomaly detection. So that's why we go with the object detection. So here's the several stages to deploy our model. So first, it's the model design. We're using the YOLO v5. This is because at the time when we're solving the application, the YOLO v5 is the state-of-the-art model for the object detection. So once we have the training data, the labeling file, and then after training, we got the models, and then we're gonna validate the performance of the model. There are some metrics, the IOU and the precision recalls. So as long as the model performance met our expectation, and then we're gonna benchmark using the original weights of the model. But there are two issues with the original weights. If we're gonna using the original weights in the production, we will see the processing time will be a little bit slower. And then also the code is kind of the hardware, it's kind of the platform dependent. For example, if we train the model using PyTorch, then we have to have the corresponding PyTorch source code to load the model and then do the inference. This also applies to the TensorFlow model as well. So in order to get rid of these two issues, we convert the trained models into the TensorRT engines. The TensorRT engines, especially during the inference time, you could improve the processing time up to like 10 times faster. And you also get rid of the platform dependency. So in order to generate the TensorRT engines, we will have the weights file. In this particular application, we're using PyTorch. So the weights file is in the .pt format. And then we're using the YAML file. So the YAML file just tells the TensorRT generator, like which model and then what's the input image dimensions to the model. And then we run everything in the container. We use Docker file and .compose to generate the engine. To automate the engine generation process, we're using some bash script. So next, let me share my screen. I can do a quick demo how to generate the engine. So that's the weights file after finish training the PyTorch model. And then this the YAML file looks like. So we're using the YOLO small model, and then we specify the input dimension, the number of classes, the batch size. And then next, let's look at the build engine script. So you will try to find the weights file. That weights file is required for the engine generator. So we're gonna, if we cannot find the weights, we're gonna convert the PyTorch weights into the correct format weights. And then we're gonna build the engine generator. If the engine is already there, which in this case it's I already generated the engine before the webinar. If the engine is not there, you will using this command to generate the engines. And then here is the doc file looks like. So we are using this Docker-based image, this because it includes the required version of the TensorRT inside this base image. And then we will install the dependencies and clone 2 repos and build a library in order to load the YAML file. This is the doc compose looks like. So it basically just loading my laptop's GPU and then run these 2 batch scripts, the build engine and benchmark. So let's look at the benchmark. So for the benchmark, you will compare the POC time between the original weights using the PyTorch, and then compare with the POC time using the TensorRT. So let me bring up the container. So it's Docker compose. So as you can see, this is the POC time without TensorRT. We can see the average POC time is around 23 milliseconds. And then in here, it's using TensorRT. We can see the POC time is significantly improved. And then, as you know, like the amount of the improvement also depends on the GPU you are using. So let me turn off my screen. So right now we have the TensorRT engines. Now the next question is how we're gonna deploy the TensorRT engines into our Gadget system. So we're gonna require the 2 files, one JSON file, another is the Python script. So here's the 2 files it looks like. So actually, let me share my screen. So let's first look at the JSON file. In the JSON file, we just tell the gadget where to find the engine, and then where's the supporting file for the engine. And then in here, it's kind of the user defined the confidence level. And then the gadget will load these confidence levels and displays them into the HMI. And then the last 2 parts are the arguments to the YOLO v5 model. So next, let me show you the pipeline class looks like. The gadget expects a certain API method, which are the load, the cleanup, the warm-up, and the predict. So let me first look at the load function. So it's just a create instance of the YOLO v5 TensorRT class. And then you will load all the configurations from the JSON file to initiate the instance. So for the cleanup, it's just detect how many models loaded into memory and then removes them from the memory and deletes them. So for the warm-up, this is interesting. We found out if we directly using the TensorRT on the first production image, the POC time for the first image will be pretty slow. So that's why we do some warm-up. In this case, we're just loading a bunch of zeros, the same size as the production image, and then feeding to the model. The model just do some inference on the dummy inputs. So this will speed up the inference time on the following images. And then the last required method is the predict. So it requires certain arguments. The first is the input image. This is the location to load the saved image. And then the config, which is a dictionary. So you map the name to a certain value. The config will have like the confidence level and then mapping to a certain, the actual value of the confidence level. Also, you will have the arguments to the YOLO model. Once the model load the image, finishing the inference, you will save the result as the annotated image. And this is the location to save the annotated image. And then next, the method will require a result dictionary. So that's one part of the API. So next, I will bring up the container to run the unit test. So Docker compose, and then looking for the pipeline test Docker compose file. So it's loading the model. Okay, so you finish running through all the tested images. In here, it will tell you like what's the name of the input image, and then what's the output image, and then what kind of defect it found, and then the total POC time. Okay, let me stop sharing my screen. So we already go through this. So next, I'm gonna launch the gadget, and then you will see the similar HMI, which was showing in the beginning of the presentation. Okay, so let me share my screen. Okay, so all the container has stopped running. So let me bring it up. Stop compose. So right now it's creating a bunch of containers. It will take a little bit of time. Okay, it's running. Let me share another window. So here's the Gadget app looks like. So it looks like the model is loading the test images and making some predictions on the images. I think that's it for today's webinar. So thank you for all the audience attention, and thank you for attending. Feel free to ask us questions if you have.